Good. Okay, guys. Page 92, please. 2, 3, 4. Yeah, great. Don, hey, come on. Which one? 5? Yeah, okay. Number 5 it is. So before we start on 92, I'm going to do number 5 from page 90. Can you see it on it? There we go. Okay. So page 5, question 5 on page 90. So here, this one a bit tricky because of what it says. It says, express the number 8 as the sum of two numbers such that the result of multiplying their products by their difference is maximal. The reason I put this one in here, a lot of these practical, not a lot of them, but most of them, in fact, practically all of them actually, they would be known problems. You know, these aren't problems I made up. These are problems you could find in most high school maths books and calculus, okay? Number 5 is actually a very old problem. And what you're trying to do in number 5 is it says express 8 as the sum. I got your message, Sultan. Come on, hurry up. Express 8 as the sum of two numbers such that the result of multiplying their product by their difference is maximal. What does that mean? Well, let me give you some examples just so you can picture what's happening here. If I said 8 is 7 plus 1, what do I get when I multiply 7 and 1? 7. And the difference between 7 and 1? 6. And that's 42. Okay, now if I said 8 is 6 plus 2, what do I get when I multiply 6 and 2? 12. And their difference? 4. And here is 48. Okay. And so on. What you're trying to do here is find a combination that makes this a maximum. So you can see it's getting bigger. So you think, oh, okay, what if I go further down? What if I try something like 4 plus 4? Well, their product is 16 and their difference is 0. So their answer here is 0. So you see I've gone too far. So there's some combination that makes this here a maximum. And it's difficult to find because the combination isn't a whole number. It's not going to be just like 5 and 3, okay? It's going to be something like 5 point something and 2 point something or whatever, okay? So we have to use calculus here, but we can find it. So I'm just going back here. So if you want to think about it like this, I'll call this here Z. And my goal is to maximize this, but my problem is that I have X and Y in it, and I should have only X or only Y. So what I'll do is I'll just replace Y with 8 minus X. Just put that in. So here I get X, 8 minus X, 8 minus X minus Y. X minus, okay, so that's nice because they, no, that's too nice. I have an extra 8. Hang on, have I done it wrong here? Oh yeah, what am I doing? There's no 8 here. I'm not thinking right yet. It's too early. Alright, here that should just be X minus Y. There's the Y. Okay. Right, so nothing cancels. That equals x by 8 minus x by 2x minus 8. I think just to make this multiplication a little bit easier, I'll take the minus out from this one and change it into x minus 8, 2x minus 8. Okay, now I'll multiply. This would be 2x squared minus 8x minus 16x minus 24x plus 64. Okay, that will be minus 2x cubed plus 24x squared minus 64x. That's the z. Now, to make this a maximum, I need to solve for when its derivative is 0. Minus 6x squared plus 48x minus 64. I want to know when that's 0. Or in other words, I want to know when 6x squared minus 48x plus 64 equals 0. I cannot divide by 3. In fact, I think I need to use the quadratic formula here. It doesn't... Oh no, I know I have to use the quadratic formula here. It doesn't have nice roots. Don't think so. Okay, so A is 6, B is minus 48, C is 64. Yeah, and I get two answers here. I get x equals 6.309 or 1.691. Now to find the y is easy because just remember that y is 8 minus x. So 8 minus 6.309 should be 1.691. And it is. So you get 1.691 or 6.309. So you get two answers. You could say 8 equals 6.309 plus 1.691, or the second answer, which is kind of silly because it's the same, 1.691 plus 6.309. So there's no need to write both answers down. So we'll not reject, but no need to write this one here. Let's see what answer we get. If I do their product, multiply their difference. If I go, do you remember the numbers I was getting at the start? It was like, I think one of them was 42 maybe, and one of them was 48. What was it?
42.
Yeah, so I really want something more than 48. Let's have it, yeah, let's see what it is. It's going to be 49, is it? Point something, 1.691 times 6.309 minus 1.691. Yeah, 49.3. So that is bigger than the numbers I was using at the start. So this is this here is the way I should express 8 as a sum of two numbers so that their product multiplied their difference is as big as possible. Okay. I said this is a very old problem. In fact, I think there's a way to do this without calculus, but it's a good example of using calculus. And I have a feeling that the way to do it without calculus is probably a lot longer. And that's actually good because the worksheet today, it's something that we've done already. So before you go on to 92, if you just quickly look back at 80. On page 80, we were finding equations of tangent lines. But now that we know how to find the slope of a tangent line, we can now find tangent lines much quicker, which is what we're going to do on page 92. Okay. No! Come back at 10 o'clock. Yes, I know. 15 minutes is too late for me. Come back at 10 o'clock. Come back at 10 o'clock. Okay, can I scroll down? Yes? Yep. Okay, so tangent lines. Tangent line. Right. Let's do a couple of these as examples. So let's say I have y equals ex and I want a tangent at 0, 1. So equation of the line is y equals mx plus c. Okay? Yes? Y equals mx plus c. The m is the slope of the tangent. That's easy to find now because that's just the derivative. What's the derivative of ex? Come on. Ex. So here we have to put in x is 0. E power 0 is 1. So that goes in now for the slope. Y equals 1x plus c. And how do I find the c? Well, to find the c, I put in this point here, don't I? Yeah. So putting that in, I get 1 equals 0 plus c. C equals 1. So now I have my answer. Y equals 1x plus 1. So you can see that's a lot quicker than the technique we saw at the start of the chapter. And as you can see with this example, you can find the tangent line for against any curve now, whereas previously we were only looking at quadratics. Okay, so I'll do some more. I just want you to practice. I want you to try number 2 for me, and then I'll do number 2 on the screen. And while you're doing number 2, I'll put the graph of what we found on the screen as well. So just do number 2. It should only take you 1 or 2 minutes. Hey, don't. Okay, do you have that nearly finished now? Okay, so this is just the graph of what we did in number 1. The blue line is e power x, and the red line is the tangent line at the point 0, 1, which you can see is right there. Okay, so we have nice tangent line at 0, 1 there, and you can see that we have the right answer, x plus 1. Okay, let's have a look at number 2 here. So this was sine x, wasn't it? Okay. Sine x, and again at 0, 0. So this is the tangent line. So to find the m, we need to calculate the derivative, which here is cos x. But we want to calculate it at 0, 0. So cos x at 0, 0. Well, what's cos of 0? It's 1. So I have y equals 1x plus c. I put my 0, 0 in. I get 0 equals 0 plus c.
C equals 0?
Yep, c equals 0. So that's the equation of that line. Okay. I think you get the idea of what's going on here. Let's look at normal now. So I might have mentioned this, but just to be really, really clear, a normal line is just perpendicular to the tangent line. So for example, actually let me go back to the graph program here. So if I take sine x, there it is there, and I want the tangent of sine x when x is 0. There it is there, the tangent line. The normal line is the one perpendicular to the tangent. So I can see in this case, I don't need much to calculate it, I can see that the normal should be minus x, because that one will be perpendicular to x, and it also goes through 0, 0. So here, let me sharpen that up a bit. Yeah, the red line is the sine, the blue line is the tangent, and the black line is the normal, which is perpendicular to the tangent. So let's do an example now with normal, which the first one I can see here is number 6. So I'll do number 6 here. We have y equals 5x squared minus 2x minus 8 when x equals minus 4. So first let's get the slope of the tangent. That's 10x minus 2. That's 10 by minus 4 minus 2. That is minus 40 minus 2. That's minus 42. But that's not the slope we want. That's the slope of the tangent. We want the slope of the normal. Well, because it's perpendicular, all I need to do is change it into that. And that's all. Now I can continue as normal. Okay, so I want to find the c. So I need to put in a point. And this usually catches people out. What do I put in for x and y? What's x? What's x? Minus 4. And what's y? No. Caught you. Very good. We don't know the y, but that's okay, because we have exactly what we need here. We have a formula to tell us what the y is if we know the x. So I just need to put minus 4 into the original, and I can get the y. So 5 times minus 4 squared minus 2 times minus 4 minus 8. So it turns out that y will equal 80. So now I can put that point in. 80 equals 1 over 42 minus 4 plus c. So 80 plus 4 over 42 is ugly. 1682 over 21. So I have my answer. Y equals 1 over 42x. I remember last year there was some problem with these questions. I don't remember if I fixed it. Is that right now? I have it at decimals. Why did I do that? Why did I do that? That's... yeah, I'm not being too accurate there in number 6, but it is right anyways. That answer is not so accurate at the back. In the exam you should keep it as fractions. Okay? Right. I'll use this one as an example for number 11 here. Okay. So I'm going to make up my own question next, but for it I need to use this, and I need to use this. So please write those down, because I'll need you to read them back to me now in a moment. Okay, can I scroll down? All right. So we've now had 2 lessons on finding tangent lines, but why are tangent lines so useful? So can you give me the original cubic there, please? What was it? It was a cubic, wasn't it? 2x cubed or something? What was the a quadratic, was it? 5x squared. Yeah. Minus 8. Okay. And what was my point? It was minus 4 and 80. So I need to, there we go. Minus 4 and 80, you know, which will be about there. Let me mark it in. Minus 4 and 80. There it is, roughly there. Now what was my, oh actually I can just get the program to give me the tangent line. Tangent, no it wasn't tangent, it was normal. Okay, so I won't use the normal here, I'm going to use the tangent. So we'll find the tangent. The tangent line when x is minus 4. Let's draw that. There you can see, there it is right there. Now, why is the tangent line so useful? Well, I'll give you an example of why it's so useful. For example, if I substitute in here minus 4.1 into my quadratic, I get 84.25. And what do you think would happen if I put the same number, minus 4.1, into the tangent line? Will I get a similar answer, a different answer, the same answer? What do you think? Different. Will it be bigger or smaller than this number? Smaller, because you can see the blue line is slightly under the red line here. So we're expecting something like maybe 84. Okay, so I sub into my tangent line minus 4.1. And I get 84.2, which is very, very, very close. In other words, tangent lines and curves, they give you nearly the same value, provided that you're close to the point where they meet. Now, why is that useful? Well, it gives you results like this. So if I go back to my sine x example, let me delete that. Okay, I'll graph this. Now, who remembers, what was the tangent line for this one? I think this was the second question. What was the tangent line? Yeah, y equal to x, wasn't it? So if I draw the tangent line now, okay, there it is there. So if we take out our calculators and put in, what's the point where they meet here? 0, 0. So let's put in a number that's near 0. So in radian mode, if I type in sine 0.1, what do I get? Well, actually, let's do it a little bit better. Sine 0.2. That's still too small. I don't want it too small. Okay, sine 0.3. What do I get? 0.295. Now, if I put 0.3 into this function, what do I get? What do I get? 0.3. Are those two values similar? Yeah. So in other words, you have, in that example, sine x is roughly equal to x when x is near 0. Physics students, result looks familiar? Yeah, flashback. So this is the reason why. Okay? In the exam, it's this approximation idea, it's not in the syllabus and has not been on the exam. So I don't think they'll ask you it. But I put it in here because this is why tangent lines are useful. So I feel like it should go into this lesson. But for exam purposes, they only ask you like how to find the tangent, not how to find, they only ask you to find the tangent line or to find the normal line. like what I did in question 1, 2 and 6. They don't ask you these approximation questions which are 11 to 16. At least they never have, and it's not on the syllabus. I don't think they will. You can try 1 or 2 from 11 to 16 if you want. They're not that difficult. Like I've just done one here. For example, if I say f of x equals sine x, and I use x as 0.3, I get, I think, f of 0.3 is 0.295. And if I say the tangent line is x, what is g of 0.3? It's 0.3. How different are these numbers? Not much. 0.005. So that's all I'm asking you to do in 11 to 16. I want you to compare the difference between using the tangent line and using the curve. They should give you a good approximation. Okay. So I think we've done 1, 2 and 6. So you really should finish 1 to 10. So there's 7 questions there for you to do, and they don't take that long to do. Okay. And then when you get 1 to 10 finished, I'll leave it up to you to decide if you want to do 1 from 11 to 16. I think it's a good idea to do one of them, but you don't have to do it. Okay? So you can start those now. And then in the second lesson, we're doing the last chapter, which is integration then. So 1 to 10 now, please. There's 7 questions there for you to do.